This week's lecture, we'll be going over when researchers should use nonparametric statistical tests and list the nonparametric equivalents for common parametric statistical tests. In addition, we'll describe the two different types of chi-square tests and compare and contrast a Spearman's rho with a Pearson's R-test for correlation. Lastly, we'll describe the basic elements of the Mann-Whitney U-test and the Kruskal-Wallis ANOVA. In order to use parametric statistics, researchers must meet the assumptions. Those assumptions are: the variable of interest must be normally distributed within a population. Second, the variable of interest must have the same variance within samples drawn from the population. And third, scores or measures for the variable of interest must be independent. Also, parametric tests use means and standard deviations to calculate either relationships or differences. They also use interval or ratio data. However, if researchers cannot meet the assumptions with their data they collected, or if they collect nominal or ordinal data, they need to perform nonparametric statistics. Nonparametric statistics are statistical tests that do not require the assumption of a normal distribution of the sample. You can see the figure to the right that the shape is not normally distributed. Nonparametric statistics offer an alternative when one or more of the parametric assumptions cannot be met. One thing though, or some disadvantages with nonparametric statistics, is that they have less statistical power, which increases the chances of deciding not to reject the null hypothesis when differences do exist. And second, fewer options exist for assessing nonparametric tests when using software such as SPSS. SPSS primarily focuses on parametric statistics. It is important to know that for every parametric test, an equivalent nonparametric test exists. When choosing parametric and nonparametric tests, there are some guidelines or questions to ask yourself to help make a choice. Here is a list of questions to ask yourself. If answered yes, then a nonparametric test should be used. This table here provides some further guidelines for selecting parametric or nonparametric tests. You can see that there is an assumption column, parametric column, and a nonparametric column. For example, the assumption of population distribution, if it is normal, then the test you would select would be parametric. However, if the population distribution was skewed, kurtosis, or something else, you would select a nonparametric test. Here's the parametric and nonparametric test equivalents based on the type of comparison. For instance, if you're looking at differences between two independent groups, a parametric test is the t-test, while the nonparametric version is the Mann-Whitney U or chi-square test. We'll go over the nonparametric tests in this lecture. One of the situations for which researchers must choose nonparametric statistics is comparison of frequencies or percentages among different categories of participants. Chi-square compares the expected frequency or distribution of values in the population based on chance to the observed frequency or distribution. Therefore, the participants are grouped into categories such as expected and observed. The statistical symbol for a chi-square test is x squared. For it to be significant, similar to the independent t-test and ANOVA, the calculated x squared has to be greater than the critical x squared value. We'll use an example of performing a one-way chi-square test. You would perform this nonparametric test to see if two or more groups differ on one variable category. So let's say a coach wants to determine if frequency of ankle sprains are different on a grass field versus an astroturf field. First, you would gather data on the number of ankle sprains on the athletes over the past 2 years. 1 year using the grass field and then the other year using the astroturf field. We can then develop the null hypothesis, which would state that ankle sprains occur at the same frequency on both of the fields, while the alternative hypothesis would state that athletes sprain their ankles more frequently on the astroturf field than on the grass field. Then we would set the alpha level at 0.05. The actual number of sprains is the observed frequency on each field. For the expected frequency, consider what you would anticipate if there were no differences between the fields. In this case, you would expect that half of the sprains occurred on the grass field and half occurred on the astroturf field. Therefore, you divide the total number of sprains over the course of the 2 years by half to get the expected number for each field. After using statistical software such as SPSS, you get an x squared value of 2.4. The critical x squared value is 3.84. So since 3.84 is greater than 2.4, you do not reject the null hypothesis and conclude that both fields yield the same frequency of ankle sprains and that any differences are due to chance. Another chi-square test is the two-way chi-square test, which is a chi-square where two or more groups are compared on more than one category of occurrence. A two-way chi-square is also known as a contingency table. This test determines if some interaction exists between group and category. We can use the previous example and expand it to see if there are any differences in severity of ankle sprain and the frequency of those severities. So the research question would then ask, does field type affect severity of ankle sprain? And you would then look at the first, second, and third degree severity of ankle sprains. The null hypothesis would state the degrees of ankle sprain and field type are independent of each other, while the alternative hypothesis would state the degree of ankle sprains depends on field type, such as AstroTurf has yielded a higher frequency of second and third degree sprain compared to grass field. This table shows the observed data for severity of ankle sprain on each field type. You can see that grass field has mainly first degree severity with 20, while AstroTurf has a higher frequency in second and third degree severity ankle sprains with 13 and 10. We can use this table and show the expected frequencies, which is calculated by multiplying the column total by the row total and dividing by n. However, all of this will be calculated for you in SPSS after you input the data. The x squared value results in 9.24, while the critical x squared value is 5.99. Therefore, since 9.24 is greater than 5.99, you reject the null hypothesis and conclude that the observed degree of sprain differs between grass and AstroTurf. The nonparametric equivalent for the Pearson product moment correlation, R, for determining relationships between variables is called the Spearman's row or Spearman's rank correlation. Spearman's row is used when the two variables are ordinal, or when one variable is ordinal and one is continuous. Another is when both are continuous, or lastly, when the sample size is small. To calculate Spearman's row, variables need to be assigned ranks. For example, you would use 1 for the highest score and 2 for the second highest score. However, when two variables have the same value, the ranks are average. So for instance, if two variables are tied for the top rank, each is assigned a 1.5, and this is due to 1 plus 2 divided by 2. If three variables tie for the third highest rank, then take the average of the ranks 3, 4, and 5, which is going to be 3 plus 4 plus 5 divided by 3, which is going to equal 4, and assign all of them a 4 ranking. The statistical symbol for Spearman's row is P. You can also see in the formula D is the difference in ranks between two paired scores, and N is the number of observations. Lastly, you can also see with the formula to the right that this is where you input all the numbers, and then for your Spearman's row to be significant, the calculated p has to be greater than the critical p-value. An example of using Spearman's row is, say, that a researcher is interested in the intensity of effort among quadriplegic athletes and the relationship between perceived physical exertion and heart rate during activity. We would then have physical exertion be determined by using a 10-point Likert scale, where 0 equals no effort and 10 equals maximum effort. The scale that is being used is ordinal, so Spearman's row is appropriate. There are 10 players, and they were tested on a 400-meter sprint around a track, and you would come up with the null hypothesis, which would state that no relationship exists between perceived physical exertion and heart rate during a 400-meter sprint, while the alternative hypothesis would state that there is a positive relationship between these two variables. So you can see to the table to the right that this kind of shows the data that is collected from each participant. This table here demonstrates the hand calculation for Spearman's row. This requires ranking both columns of data, squaring the ranks, and then totaling the squared ranks using the formula. However, SPSS will give you the calculated Spearman's row. The calculated Spearman's row is 0.66, and the critical value is 0.450. Since 0.66 is greater than 0.450, you reject the null hypothesis and conclude that there was a significant correlation between perceived exertion and heart rate during a 400-meter sprint in quadriplegic athletes. The interpretation of Spearman's row is the same as for Pearson's R. It has either a positive or negative relationship, and also the value ranges from -1 to +1. Again, 0 is going to be no relationship at all, and a -1 or +1 is a perfect relationship. After you determine significance, you can square a row to get a value of meaningfulness or strength of the association. In this case, we will use 0.66 and square it, which gives us 0.44. And this indicates a markedly strong relationship in that 44% of the variance is explained by the relationship between those two variables. Non-parametric tests for group differences exist that researchers use in place of parametric tests if violations to the assumptions are present or the sample size is small. The first one we'll go over is the Mann-Whitney-U test. This test is the non-parametric equivalent of a t-test, which is used to compare two groups. The Mann-Whitney-U is a test that uses ranked data just like Spearman's row, and then determines if the ranks of one group are different from those of the other. The scores are ranked across the entire sample. The statistical symbol for the Mann-Whitney-U test is the letter U, and for it to be significant, the calculated U has to be greater than the critical U value. And you can see below is the formula for calculating Mann-Whitney-U. For the Mann-Whitney-U example, a researcher wants to determine if 100-meter sprint times differed in quad rugby players using an Eagle Tornado or a Vesco Metalcraft rugby chair. Based on the table to the right, 7 players used the Eagle Tornado chair and 6 players used the VMC chair. The null hypothesis for this example would state that 100-meter sprint times would not differ between the Eagle Tornado and the VMC groups, while the alternative hypothesis would state that groups will differ in their 100-meter sprint scores. For the Mann-Whitney-U, you'll first want to rank the data with 1 being the fastest time and then so forth. After calculation, either by hand or through SPSS, the calculated U is 25. The critical value of U is 36. So since 25 is less than 36, you do not reject the null hypothesis and conclude that the time in the 100-meter sprint is not significantly different for the two types of wheelchairs. When there are more than 2 groups to compare, researchers can use the Kruskal-Wallis ANOVA, which is a non-parametric equivalent to the one-way ANOVA. So you'll interpret the Kruskal-Wallis ANOVA just as you would with a one-way ANOVA. With the parametric one-way ANOVA, rejecting the null hypothesis indicates that differences exist between 2 of the groups, but the results of the test do not indicate where those differences exist. You would then need to perform a multiple comparison test to see where the differences occurred. This goes for the same for the Kruskal-Wallis tests. Similar to the Mann-Whitney-U, you need to rank the data and then compare the sums of the ranks. Because of this, the Kruskal-Wallis is an extension of the Mann-Whitney-U test. In general, use the test as you would in ANOVA, except the data does not meet one or more of the parametric assumptions. Things that need to be completed by Monday, December 7th by 11:59 p.m. is the non-parametric assignment. Lastly, Exam 2 or your final exam will be due by Tuesday, December 8th by 11:59 p.m. Exam 2 or your final exam will be available starting Monday, November 30th.